All right. Hi, everybody. So I'm just going to go over the homework quickly. Please make sure that you are making corrections as we go through. So your homework last night was the vibrations and waves review sheet. I'm going to post the answer key as well, but just make corrections as we go, all right? So number one, what is the period of a pendulum that takes 1 second to make a complete one back and forth vibration? What this question is really asking is, hey, do you know the definition of a period? And what the period is really the cycle time, or the time needed for one back and forth swing or one back and forth complete vibration. So if the period or the pendulum takes 1 second to complete one back and forth vibration, then the period is 1 second. Number two, suppose that a pendulum has a period of 1.5 seconds. How long does it take to make the complete back and forth vibration? Well, the period is 1.5 seconds, so the amount of time needed to complete that back and forth vibration is 1.5 seconds. Number three, does a pendulum with a 1.5 second period have a longer or shorter string than the pendulum with a 1 second period? Well, because the period is longer for the 1.5 seconds than 1 second, so the pendulum with the 1.5 second period has a longer string length. Okay, so the period of the pendulum is affected by the length of the string. It is not affected by the mass. And so therefore, in order for that thing to pivot and pivot at a slower rate, it needs to have a longer string length. The one with the shorter string length is going to go back and forth much more quickly. So it's going to have a shorter string length, so a shorter period. So for number four, we had to label the amplitude, the crest, the trough, and the wavelength. So kind of going through amplitude, it is the amount of energy within your wave, and we measure it from either the midpoint up or the midpoint down. I chose in my graph to do the midpoint up, so I represented it in green. The wavelength we can show as one complete waveform. We can measure it from crest to crest. We can measure it from trough to trough. I chose to do it as one complete waveform, and it is shown in red. And then the crest is the high point of the wave, and then the trough is the low point of the wave. So number five, how many wavelengths are shown in the diagram above? So you can see that one complete waveform is here, so that's one, and then another complete waveform is shown as well, so that's two. So two complete wavelengths are shown. Number six, distinguish between period and frequency. So the period is the amount of time it takes to complete one back and forth vibration, and the frequency is the number of vibrations over that period of time. So your period is 1 over f, and then your frequency is 1 over your period. So number seven, does the medium in which a wave travels move with the wave itself? Defend your answer. No, it does not, because waves cannot carry matter. Number eight, this is our equation to solve for wave speed, and it is how wavelength and frequency are related. So in order to get our wave speed, we're going to do our wavelength times our frequency. We can also put it into a triangle in order to solve for either all three of those variables. Number nine, as the frequency of the sound is increased, does the wavelength increase or decrease? So we saw a video on this, but as our frequency increases, our wavelength is going to decrease and vice versa. And that's because it is an inversely proportional quantity. And so we saw a video where when we got to a higher pitch sound, it was a shorter frequency. So, a higher frequency, so a shorter wavelength. All right, number 10, distinguish between a transverse wave and a longitudinal wave. A transverse wave is a type of waveform that's going to disturb the particles perpendicular to the direction of wave motion. And so we saw this yesterday with our lab. We saw it as a demonstration, but basically we have to move our hand opposite to the waveform that we want to create, so 90 degrees too. A longitudinal wave is the type of wave whose energy is transferred parallel through the particles in that medium. So again, in the same direction as. All right, so transverse, 90 degrees, longitudinal, parallel, or in the same direction as. Number 11, distinguish between constructive and destructive interference. So constructive interference is when two in-phase waves are going to meet. So this would be like a crest meeting a crest or a trough meeting a trough. And so when they are in phase like that, we're going to have an increase in our amplitude. Destructive interference would think about like destroying something. This is when we have two out-of-phase waves that are coming to meet one another. So maybe like a crest meeting a trough. Okay, and what happens is the resultant wave is a cancellation of both of those things. Number 12, is interference a property of only one type of wave or all types of waves? It's going to be a type of all waves. And we're going to see it more next cycle with sound and with light. Number 13, what causes a standing wave? So a standing wave is when the propagation wave, or like the primary wave source, is created and the reflection back on that primary is the exact same frequency and speed. And so what's created is what we call a standing wave, or a wave that looks like it's not moving at all, where it has nodes that are right on the midpoint and antinodes, which are on the crest and the trough. Number 14, when a wave source moves towards a receiver, does the receiver encounter an increase in wave frequency, wave speed, or both? So this has to do with the Doppler effect. So when we have a source a source that is moving towards the receiver, what that means is that the source that's creating this vibration is moving towards something that is observing that vibration. And if it's moving towards the person that's looking at it, then the frequency is going to be seen as an increase. Okay, so we saw this with like our train coming at us or the car horn coming at us. That was an increase in wave frequency. However, the speed of that wave does not change, right? If we were hearing that sound, it's still going to travel at the speed of sound. If we were seeing a light, it's still going to travel at the speed of light. However, the frequency, or how we visually see it or hear it, is going to change, right? If it's the source is moving towards the receiver, then the frequency is going to increase. Number 15, does the Doppler effect occur for only some types of waves or all types of waves? It's going to be all types of waves. Again, we're going to see it more next cycle with sound and light. Number 16, compared with the speed of water waves, how fast must a bug swim to keep up with the waves it produces, and how fast must a boat move to produce a bow wave? So if we want the bug to remain at that water line, or the speed of the water wave, then we need the bug to move at that speed, right? It can't go faster, it can't go slower if we want that same propagation to happen. If we want our boat to create a bow wave, or that two-dimensional V-shaped wave, then that boat needs to travel faster than the speed of that wave. All right. And so distinguish between a bow wave and a shock wave. So a bow wave is a two-dimensional V-shaped wave that's created when an object is moving faster than the speed of that water. When a shock wave is created, a shock wave is a three-dimensional cone-shaped wave that is produced when an object is actually moving faster than the speed of sound through the medium. So we saw a couple of videos where we had jets that were moving faster than the speed of sound through air. And so we saw that actually happen. We heard it happen, like we saw the visual airplane moving, and then we heard that sound, right? So that would be an example of a shock wave. And a sonic boom, it is the sound that's actually generated, like that loud snap that you hear when something is moving faster than the speed of sound. Part B, how fast must an aircraft fly in order to create a sonic boom? Well, they have to be moving faster than the speed of sound. So in this class, the speed of sound is 340 meters per second. That's going to vary depending on the temperature and the pressure in which we're looking at it. But it's about 770 miles per hour, just to kind of get that frame of reference. Number 19, what's the wavelength of the sound wave traveling at 340 meters per second with a frequency of 440 hertz? In order to solve for this, we needed to use our little triangle for our wave speed, frequency, and wavelength. You can solve for the wavelength by dividing your velocity divided by your frequency. So 340 divided by 440, you're going to get 0.773 meters. If you round it a bit different to like 0.8, that's fine. Number 20, we had to look at the resultant, if it was constructive or destructive. I tried my best to draw these, but basically because these are two crests that are going to meet, then it would be a constructive interference pattern that's going to happen, or basically there's going to be a larger mountain. And then for destructive, it wouldn't show with these two interactions because, again, we're still showing two crests coming at one another. But what I was getting at here is that if we had a crest and a trough meeting, or something that was lower, then a destructive interference would be just like a straight line. Okay, so that was our review sheet. If you have questions, please feel free to email me. I am still available through email, and I hope you all have a great day.